Hi guys, welcome to Failtober week 4. This is my favorite week, I think, of the entire series. So we are going to be talking today about what you actually do in the classroom when you have an epic STEM challenge failure, or I'm going to even talk a little bit about labs or experiments as well, because this is really where all this work, all this foundational work that we've been talking about throughout the whole month, with working on your own mindset and your students' mindset, this is where you actually get to put it into practice and see where the weak spots might be and where you might need to build up some of that resilience and grit and determination, right? So this is actually the super exciting part, and it's the part we often actually underestimate and miss out on if we don't sort of set ourselves up to capitalize on the failures as they happen in the classroom. So this is probably the thing I'm most excited about. So I'm going to actually throw this piece off just so I don't see it. You can still see it in the other corner. So this is mostly about Epic STEM Challenge fails, but we are going to be talking about putting it into practice with labs and with experiments as well, because these are the areas where I think you have the highest possibility of having the students fail within sort of a short period of time, or having several of them come up against some problems, right? So let's start with like labs, okay, or experiments. So I think I mentioned in the first of the Failtober series that I had sort of an aha moment years ago. I was teaching second grade. We were doing this bean experiment. We were trying to grow beans, and each group had a different thing they were experimenting with. So that somebody wanted to see if it made a difference for the bean plants, if they watered them, and we were growing them from seeds. If they watered them with, milk or soda or water, and some of them were testing light, and some of them were testing soil types. There are all different things going on in the classroom, but none of the seeds grew. None of them. And I was, after like a week and a half, I was realizing, oh, there's like nothing happening here, and this is horrifying, and I've made like a huge mistake, and like I just wanted to, like, if I'm honest, what I wanted to do was just chuck the whole thing, just throw it away, and like pretend it had never happened. But I obviously knew I can't do that as a teacher. That doesn't make sense. And luckily, I had this like moment where I just thought, what would a scientist do? And I thought they wouldn't just chuck the whole thing and pretend it hadn't happened. I actually had a friend who sent a book to me recently, and I don't remember the exact quote, but if I'm going to paraphrase it, when you're met with, a failure, you should approach it like a scientist would. Would you expect that after a failure that, a scientist would be like huddled in the corner of the shower crying? No, that whole thing is like absolutely absurd. Hey, Tammy. And actually, Tammy's the one who sent me the book that I'm talking about. So thank you, Tammy. That ebook was awesome, and gave me some really good points for this as well. Exactly what would a scientist do? So I had that thought. So I know that the beans were supposed to grow. I know that. But do scientists always know what is actually supposed to happen in their experiments? They don't much of the time, right? So we're sort of coming at this as teachers with like the answer key in mind. And what we want is for our students to be able to exist without the answer key, because scientists, if we want them to think like scientists, we have to expect that they're not going to have the answers up front, right? So this is where some of our sort of STEM ideals come into play. Let me pull those in for a second. I know you can't see all of those like super well, but this is one of the things we covered in the second week. We're talking about STEM ideals. So when this experiment, when it didn't go as it was supposed to go, and again, I knew how it was supposed to go, but the students didn't necessarily know. I mean, they figured, they're bean plants and they're plants, so they're supposed to grow, right? But as second graders especially, they could easily have just thought, oh, well, all of these things didn't work, so these things don't lead plants to grow. So I couldn't have that, and we couldn't have the idea of just like throwing it away and pretending it didn't happen. Sweeping failure under the carpet doesn't set my students up for a good, healthy relationship with productive failure. So instead, I wanted to work on some of these STEM ideals with them, thinking about, and I think I actually literally asked the students, we all sat down on the floor, and we had this, this discussion. I noticed the plants aren't growing, and I thought that they would grow by now, at least some of them. So, what would a scientist do? in this situation? What would a scientist do? And you'll be surprised, even second graders come up with really amazing answers, for that question. Well, maybe they would just try again. Or, we talked about, what did you think would happen? And they would, they went back over what their hypotheses were. And we talked about why might the seeds have failed. So we'd be going through these things like analyze and ask why, making connections between things. So we went through and talked about maybe we did something wrong when we set it up and we didn't know that we did something wrong. Like, it's not a bad thing. One of the things you really want to do is you want to capitalize on this idea that you can remove the shame. And like, kids that young don't even really have the shame there. We put it in there because of our own issues, which is why we started Failtober with thinking about our own mindset. And that's come into play every single week this month, and it will throughout, because the way that you come to the activity, the lab, the experiment, the STEM challenge, your feelings about failure are definitely going to be modeled in one way or another. Whether you do it intentionally or unintentionally, they're going to see that. So what you want to do is, before you even start, hey Angie, before you even start and you go in, I always have to check my mindset. And I've been doing this a while, right? And I still have to check my mindset and remind myself, before I go into this lab, experiment, or challenge, I should expect that failure is a possible outcome. And then now I've gotten to the point where I think, now I'm just not even just like steeling myself to like prepare myself for potential failure. I now think to myself, and what a gift that'll be if they do fail. Like, it's, what if it is a gift? And what if we can look at it as being almost more excited about the potential for the failure lesson than if it all goes swimmingly according to plan. And that has really changed not only the way I approach a lesson, it's also, I think, impacted the way my students approach their work over time. Once I sort of was able to make that leap of like, it's going to be okay if it fails. And I'm going to be actually maybe more excited if it fails. So let's talk about what you actually do. Okay, so what do you actually do in a situation when it's actually going really, really south? I just gave you the example with the experiment, or with a lab, you can do the same thing. So like, I would say to the students, I would ask them in a case of a lab and experiment, what do we expect to see happen versus what actually happened? And what are some of the potential reasons that it happened, right? Maybe we got a bad batch of seeds, or maybe we needed to start the seeds and get them to grow to a certain level before we actually move forward and then plant them and then test them. We need to make sure that we can validate that the seeds wanted to grow at all before we, started testing them against each other for these different variables, right? And exactly, Angie, that's where the perseverance does come in. And so that's why I pulled up the STEM ideals in general, was just to kind of point out that a lot of these are going to be sort of interplayed in what we're doing today. So it's not just embracing the idea of productive failure, but pulling in these other things. What would a scientist do? How would they approach this problem, right? Because, and this is the key thing, and maybe this is going to be so obvious for you, but it was so revelatory for me, was just having that moment of, what would a scientist do? Because the scientist doesn't have the answer key. The scientist doesn't know what was supposed to happen. And I want my students to be able to work through as though they were a scientist. What if there were no books starting tomorrow? What if the internet went away starting tomorrow? Would we be able to recreate the knowledge of humanity? That's what I want, right? I want my students to have that sort of like the perseverance, the grit, the determination, but also the analysis and being okay with saying, okay, well, this didn't happen the way I thought it would. This is what I thought would happen, and it didn't. So what do we do next? What are the next steps now? And what that will sometimes mean in terms of labs and experiments is you might not do as many of them as you thought you would, right? And that's okay. Like, we have to be able to be flexible enough to pivot, right? And teaching our students to think scientifically and use their reasoning, that's an important part of the standards that often we don't always feel like, I'll speak for myself. I didn't always feel like, I'm not really sure how I assess that, or how in some cases, in some cases it's easy to see where to assess it. But for me, the best way is to see what happens with a failure. And then how do they react to that? and learn from it and apply that in the next whatever iteration of that lab or whatever. So you might do fewer, but go deeper, particularly when there is a failure, because they don't know what's supposed to happen. And you knowing what's supposed to happen is almost cheating, right? In a way, when we think about it in terms of like building that scientific reasoning. So I want to sort of pivot right now into STEM challenges. There is one quote I didn't have the quote written down, but it's something that Asimov said, Isaac Asimov, and he said something along the lines of the best or most interesting scientific discoveries don't start with eureka. They start with, that's interesting. So I always like to sort of go into a lab, an experiment, or STEM challenge with that attitude of just being really interested in all the things that happen, whether they're what I thought they were or not, and almost being more fascinated if it's not what I had expected. So let's talk about STEM challenges, because I know that this is a thing that comes up for me a lot. I'll see in my feedback, I'll get in questions from different people all the time, about, or frustrations even from teachers, like that a challenge didn't go the way they had anticipated, that, or the students struggled more than they thought they would. And sometimes I'll hear from a teacher that sounds really enthusiastic about that. Like, oh, it was more challenging than I thought it was, and my kids really rose to the challenge. And even though they didn't do well, they were engaged and they were trying and they were interested. And then I'll get the flip side though, and I'll know that some of these teachers have the same issues that I used to have and continue to fight a little bit with the idea of failure being a good thing. So I'll get some things from teachers that say, this was just too hard for my students and they didn't like it or whatever. So I know this is a thing that a lot of people want to know, like, what would you do? Like, what would I do and how do I handle it? If I give a STEM challenge and it looks like it's going to be pretty widespread failure, and that will happen, and that should happen sometimes, because you're going to be setting up your criteria and constraints list in a way that the challenge is challenging. It shouldn't be so easy that there's just no chance of it to be a failure, because then it's not a STEM challenge, it's a STEM party. I don't know. If they're going to have no problem and breeze right through something, I'm just not sure what the point is, right? You're missing a lot of the rigor and a lot of the benefit that you can get out of it. So first step, always your mindset. Before I even tweak my criteria and constraints list, I check my mindset again and remind myself that I want to set the criteria and constraints in a way that is right where I think, like, right pushing along the border of what I think they can do, and maybe just a little bit past that. If my students have had many, many STEM challenge successes recently, I might set up what I have called in the past an impossible challenge. So an impossible challenge is one where I just can't even conceive how it would be possible in any way for my students to figure out how to be successful. So like an example of this would be, like the infamous egg drop challenge. If you give them nothing but soft materials and they have to drop the egg from like a pretty tall height and keep it from cracking, and you, as the teacher, can't figure out how you would do it and keep the egg safe, that's an impossible challenge. That isn't the only one. You can set up most any challenge to be impossible just by changing the time constraints or the materials, even if you don't change the overall goal of the challenge itself through the criterion constraints. You can change the materials and make it so it's almost impossible to do. Now, I don't do that every time because I don't want them to be set up to the frustration point every single challenge. But I just want to bring up this point, is that I always check my mindset first. If they've had a string of success after success after success, that's great. But now I want to push them. I want to see, what do they do when they're actually tested? We could be studying these STEM ideals that you see over here all year long, where they're looking at examples of what do scientists do? How would they react? How did they react? What struggles did they encounter? And what obstacles did they overcome? They can do this all day long and all year long and still never really embody the ideals if we don't put them into situations where they need to be tested. So you might occasionally want to set up an impossible challenge, but I find that it organically happens when it happens anyway. At some point, there will be some challenge just because of the way the planets align and the way you might have set up your criterion constraints list, where you have a large, maybe majority of your students, the groups are not doing well. They're struggling to create the challenge. So what you are doing during the challenge, wait, back up. One more thing with your mindset before the challenge starts and before you've done your criteria and constraints list is just remind yourself that the potential for them to fail is not only okay, it can be very exciting, and it can set up some of your best lessons of the entire school year. And if you truly want your students to act like scientists, think like scientists, develop those growth mindset skills, we have to put them in positions where they're going to be tested and where they have the opportunity to recover and show that growth, right? So this is an opportunity. So just remind yourself before you start, if they fail, it's not only okay, it's a great opportunity for another lesson. Okay. So soapbox, move that out of the way. So what I do when I'm facilitating a STEM challenge, I'm walking around. I usually give them, let's pretend in this case that they have 20 minutes to build whatever they're building, okay? So I'll give them the first 5 minutes or whatever just to work in the group. I don't even walk around at that point. I just sort of give them a moment to sort of kind of get with their group and talk about their designs and make their decisions about what they're going to start doing. I give them a chance to work, basically, before I start going around and asking them to tell me what they're doing. So maybe 5-7 minutes in, I'll start circulating, kind of watch what they're doing. And maybe at like the 15-minute mark in a 20-minute, 25-minute build challenge, I might notice that the groups are struggling mightily, right? I might see that it looks like none of the groups are going to be successful, by the 20-minute mark or the 25-minute mark. So I have some decisions to make, right? I want to be able to be flexible and change my plans when it looks like they need to be changed. So there are a couple of things I consider. One is, do I think they're getting close? If I think they're getting close to figuring out something that'll work, I might just say, you know what, I can see we need a little bit more time on this. I'm going to set the build time. I'm going to give you an extra 5 minutes. So maybe I give them a couple extra minutes so they have more opportunity to be successful. Another thing I do is I do what I call taking the temperature. So as I'm walking around and the groups are telling me what they're doing, what they've tried, what's working, what's not working, I'm listening to hear the frustration level. So in a situation where it looks like most of the groups are not going to be successful, if they're working and they aren't terribly frustrated, they haven't hit like max frustration level, maybe they're a little frustrated, maybe they're a little annoyed, maybe they're not at all, because maybe some of them have embodied these STEM ideals, so maybe they're working away and they haven't figured it out yet, but it's not like taxing their soul, you know what I mean? Then I just let them go. We can get to the 20-minute mark, call time. If nobody's been successful at all, but they haven't hit that super max frustration level, that's okay. Because we're going to cover what to do in the discussion part of this. So if they are working away and it just doesn't seem to be going well, but they don't seem overly emotional about it, I just let it go. And I'm going to tell you what we do in the discussion part in a second. But let's say it's 15 minutes in and I had planned to give them 20 minutes, and what I'm seeing is just like just a ton of kids who have like basically given up. They have checked out. They hit the max frustration level, and it's not productive to let the next 5 minutes run. It's not going to produce anything more. In fact, if anything, it might make things worse, right? In that case, what I do is I call timeout, because again, we want to be really flexible and be able to react to what's happening in our classrooms. So don't feel like you need to let it go exactly how you had planned it. I would stop them at that point. I would do a gallery walk to let them just see like what's going on in all the different stations around the room. So they can see what the different ideas were, maybe that had been tested, if there was any level of success or not. And then we come down and we do our discussion. I'm going to give one more example before I get to discussion questions, because in all of these cases, whether I let it go to the end and call time and then we discuss, or I just call it early and we move to discussion, the discussion questions are basically going to be about the same. But there's one other situation, right? Because you might not have like every single group has failed. You might have one group has figured out something that looks like it's going to work, and maybe all the other groups don't. So you might just have like a majority's failing and you've got like a small minority that sort of figured some things out. In that case, what I would do is I might call a timeout, do a gallery walk. They don't talk on their gallery walk, by the way. I know I mentioned that before. Gallery walks, the rules are they have to hold their arms like behind their back and like clasp their elbows so they don't touch anything. And they walk around silently and they look. And then I might go back to their groups and restart the time. so that the groups that were not successful got an eyeful of a couple of groups that might have had some ideas, and then they can get started on those ideas. Remind me to come back to it if I don't. The idea of like if kids are like, oh, but that was our idea and they stole it. I will come back to that after the discussion piece. And if I don't, somebody comment, please, because sometimes I don't always keep myself honest on that. Okay, so let's talk about the discussion question. So what do we do now that we've gotten, everybody's okay, it didn't go very well, right? I will do a whole class discussion, and I will bring them down to wherever. You know, if we have a carpet, we'll do a carpet. If we're not in a room like that, then we'll get in our desks or whatever, and that's fine. And I remind myself, and I remind them, that science is 99% failure. And I remind myself in my tone that if I want them to get the idea that life is not going to be easy all the time, right? I don't want to set this expectation inadvertently that the things you encounter in life should be easy for you. And if they aren't, then there's something wrong with that or something wrong with you. And if you get mad, if you get frustrated, if you say there's something wrong with this challenge, you know, it must not be possible, you know, this challenge is too hard for fourth graders, you know, if you allow yourself to go down that path, you may inadvertently be reinforcing this idea that I think is prevalent throughout our society, that things should come easily to you, and if they don't, there's something wrong with it or you. You are dumb, you're not smart. Or this thing was just bogus from the beginning, so it's wrong, right? And we don't want to do that. So instead we need to think about, well, how do I reinforce what I really want them to believe and what I want them to know, which is I want them to think like scientists. I want them to analyze. I want them to ask why. And this is, by the way, a reason I don't grade the STEM challenge designs. This is one of the biggest reasons I never give them a grade on the actual design, because I don't care about the design. I grade on the reflection and the analysis that happens afterwards. So whether you are successful or not is neither here nor there. It's process over product. And, you know, if Edison's team had been graded on their first iteration of the light bulb, that would have been a problem, right? They would have been called failures 10,000 times, you know, and that is the thing I really want to get forward to my students, is that idea of it really doesn't matter so much what you produce in this iteration, it's what you learn from it. Whatever we're doing, it doesn't matter what you actually made, it matters that you can look at it and think about it and use logic and reason and asking questions and get something out of it. And as long as you're doing that piece, that's what I really want. That's the beautiful thing, like the little diamond I'm trying to create, right? And I was not even say create. I'm trying to get them to create the little diamond, right? I'm just trying to give them the opportunities, like to mine for those diamonds, okay? So here's what we would do in a discussion where many of the groups had failed, if not all of them. So we'll talk about, tell me some of the things that you tried, you know, and they'll tell me, and maybe I'll ask, why did you try to do that? Or what made you try to do it that way? Or what made you think of that idea? Because I want them to start, sometimes they don't know until they start talking through, you know, they did this thing this way. Why did you do it that way? And they have a reason. Sometimes they don't. Sometimes maybe they did, but they can't figure it out. Like they can't put it into words why they thought that. But we can start making some good connections that way of, oh, well, I had seen this thing, you know, maybe they're building a tower or something. I had seen this tower that had this shape before, so I was trying to emulate that shape, or I was trying to create something that looked like that. And I thought it would work because it worked in real life. Maybe they say something like that, right? And then we might go through, okay, well, how is this? So maybe, you know, maybe why, what are some possibilities or some reasons that it didn't work the way that you thought it would? And so in that case, they might say, well, you know, in this building, you know, they had more time, they had more rigid materials, they had experts working on it, they had like the correct measurements or whatever, you know, and we were doing things haphazardly. There could be all sorts of reasons, right? But we're just starting to work through thinking. I'm just trying to talk them through. I'm trying to just ask them a question without, the only emotion that I have is just intense curiosity and interest. And like, I wonder why, yeah, that makes sense. I would think that that would work too. What are some reasons that maybe what are some possible reasons that it didn't come together the way that we thought it would? and just start talking through it. And you will see that even if they were very emotional and frustrated before you start the conversation, that you modeling the tone of this. Remember, we're going to think like scientists. And you just tell them, remember, we're going to try to channel our inner scientists, and we're going to try to think it through the way that they would, because it's okay that it fails. And the more you do this, the more comfortable your students get, because they're seeing this positive modeling and they're seeing this positive conversation where it really was okay that they failed. It has to be okay. You have to cultivate a classroom where it's safe to fail and where they have an opportunity to recover. And we're going to talk about that too. The opportunity to recover is key in this, because it's definitely a step that I think you could easily skip, and it would be a shame. Okay. So other questions I would ask them: do you think this challenge is even possible? Is it possible to build the tower using these materials in this time? Is it possible to, create something to protect this egg from a drop that high, with these materials? And, you might get yeses, you might get nos. Whatever they say, I usually, there's almost always a follow-up question, and it's hard for me to tell you exactly which ones without having the actual discussion happen, but I often will just be, for you, channel your inner toddler, right? Your inner 5-year-old, and just like, why do you think that? Tell me more about that. What made you say this thing? A lot of it's just follow-up questions of like, okay, well, why? And again, the most important thing for you is your tone, in order to encourage your students, right? So some other things I ask: what would you need? What do you think you would need in order to increase your odds of success on this challenge? And so your students might tell you something like, well, we just need more time, or I need a chance to research XYZ. Or they might say, I really wish that I had had a paperclip, because I think if I had had a paperclip, I could have blah, 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 blah. Let them tell you whatever it is they think they need. And for some kids, they might just say, like, I just need to tinker for a while. Like, I just need to play with it for a while without there being a time constraint to sort of figure it out. Now, you don't have to give them any of these things that they're asking for in their next iteration. So you decide, you consider, right? You might decide, that the timing is going to stay the same, but maybe we'll retry this challenge in a week from now. So if they really want to tinker, they could do it. They might be an early finisher on something, or they could do it at home. You might hear them say they want a paperclip and think like, yeah, I'll throw a paperclip in and see what happens. You don't have to change the things that they ask for, but you'll probably want to think about one or two little small changes that you could do. And you might need to give them some suggestions too, but I always try to get their ideas first. And then maybe, one of the things that doesn't always come up is the idea of researching something. So I might say, like, is this like anything else in life? Can you think of an example of something in real life that is like this challenge? And then we'll say, like, oh, maybe I wonder if it would help to do any research on that. Maybe we'll see if we can find some time for that on Friday during center time, whatever you got, like, oh, maybe we'll make that like an extra credit thing if you have some extra time for homework, whatever. And I also asked them, what were your biggest obstacles or problems during the challenge? And that's really an interesting one to ask, because a lot of the time, they'll tell you like, oh, well, I had folded the paper too many times, so then it wouldn't keep its shape, So like some of it'll be about how they manipulated the materials, or they might say, well, my biggest problem was I only had 12 inches of tape and I used it all on the first idea, and the first idea didn't work. So then when I got to the second idea, I didn't have any more tape, right? So some of it'll be how they approached things and how it didn't work initially. And some of it, they'll start to realize my biggest problem was that I got mad, and then I got frustrated, and then I couldn't think clearly, so they'll start to make those connections that some of the problems are things that they did, some of the problems are ways the challenge is set up, some of the problems are mindset. And that's exactly what we want, right? We want to set it up in a way that they'll start to sort of piece these things out. And so that then, okay, well, now we know what our obstacles and our problems were. Let's say we do this challenge again next week. Let's say we'll redo it in a week from now. What should we plan to do differently to increase our chances of success? And then we go back over. So even though I've asked those other questions that have already sort of like laid that out, It's like a review almost of the discussion. Like, okay, well, between now and then, we should do some research. When we do the challenge next week, we should remember to like just be calm and it's fine. We're okay. And the thing that I wanted to really bring up is that when you have a challenge where many of the groups, if not all of the groups, fail, this is when I think the second iteration of the challenge should really be a whole class second iteration. I don't always do all of my STEM challenges as whole class in round 1 and whole class in round 2. But when there's a large degree of failure, always. And part of that is I want to show them that it is important, that I value the persistence, the determination, the trying again. And I'm willing to devote a whole other section of class time to it that I might not have planned to previously. Now, I always, if you've watched me at any point, I'm always talking about you should always be trying to do multiple iterations regardless. There are just other ways to do the second iteration. If you had like a large degree of success, I still want the students to do a second iteration to apply any learning that's happened in between with related lessons, and also to just improve on their designs, because that's part of the engineering design process, is the actual iterative process of improving your designs, just like you would do with drafts of writing. But sometimes I'll let them do that in smaller centers, or as extra credit or as homework. I might send them home with materials, have them do it with their families or whatever. There are many, many ways to do the second iteration, but when there's been a lot of failure, you want to do the second iteration whole class because you want to be there to see the differences. You want to be there to lead a discussion at the end. You want to be there if they need extra support during the facilitation phase. So what that will sometimes mean is you might have maybe you had planned to do 2 or 3 STEM challenges this month, but one of them didn't go very well. So now you're going to do 1 or 2 because you're going to take one of the ones that you were going to do out and give that second week that you were going to try a totally new STEM challenge and say, no, we're going to do this one again. You can let more time pass than that if you want. I probably wouldn't let more than a month go in between a big failure and then revisiting it, because again, we want to communicate the message to students that when you fail, you don't just sweep it under the rug and pretend it never happened and move on with your life. When we fail, we take a lesson from that and then we try again. So that it's so easy to skip it because our instructional minutes are so precious and so few, that I know it's very tempting to say I just want to move on to the next thing, and we had a great discussion and I think they really understood. But if your actions don't match that discussion, if your actions say, yes, we had a good discussion about it, that's better than not doing that at all. That's certainly better than nothing, but it's not nearly as good as saying, okay, we had the discussion, it didn't go as we planned. Here are some ideas. Here's what we're going to do next to have a higher degree of success as a probability for our next iteration. And in between, whether you do it the next week or 3 weeks from now or 4 weeks from now, do those things that you guys had laid out, right? Do some research, do some related lesson planning that might help. Maybe you're going to tweak your criteria and constraints and or your materials, but you also want to go to your STEM ideals. You also want to review some mindset stuff. You also want to bring in some good quotes from your STEM professionals, or all these failure quotes that I've been putting up throughout the month. You have those now. You have access to all those on Facebook, Instagram, and I know a lot of you have picked it up through being subscribed to the newsletter. So you have all these things you can bring in, but you want to also bring up, especially if they had hit that frustration level where they were so mad they couldn't keep working, then you also have some mindset work that needs to happen between now and the next time they do that iteration. And again, a lot of it's your modeling. A lot of it's going to be how you come to the failure and just like, you're cool, calm, and collected about it because it's really not a big deal. Not only that, it's to be expected because in science, a lot of our tries are just not going to work the first time, and that's normal. And that's what we want them to think. It's absolutely normal for it not to work the way we thought it was going to. We just have to then respond to it. Not just like, oh, well, it didn't work, done. We have to respond to it, react to it, and then figure out how to improve and learn from it in the next iteration. So let me just see if there's anything else there was something I said I was going to come back and talk about. Oh, they stole my idea. Okay. So so in a case where sometimes I'll say, maybe sometimes I'll have a situation where, let's say there are 6 groups in the class, right? 5 of them are doing fine and 1 is just on the struggle bus, right? So in a case like that, I won't call a timeout for everybody, but I'll say to that one group that's on the struggle bus, I'll say, like, let's pause for a second. I want you to just, as a group, just quietly, silently even, just walk around and visit each group and just listen in and just see what they're doing. And then come back and then talk to each other and see if there's something you liked or something you thought you might want to try or apply in your design. So I will let them do that. Now, the first time you do something like that, the other groups are going to protest, most likely. It usually happens, right? And they might not protest in the moment, but they will if they see after the fact, like when they're doing their presentations, they see that a group has basically copied them. So what I do in that case, first of all, I tend to validate whatever it is they're feeling. And that's true of the frustration too. Like I'll tell them if they were, the groups that were failing and they were very upset about it and frustrated, I will validate that. I don't try to make it like they shouldn't feel that way. Or even like when I often say like, oh, well, what would scientists do? Or, what do STEM pros do? It's not that they're superhuman, that they don't feel frustration. So, I think it's fine to acknowledge that emotion and that it's a normal thing to feel. But then, then we need to move past it and figure out how to do that. So the best way to do that is to use logic and reasoning and analysis, and try to learn something from it, right? So in this case, when a group is saying, oh, well, they copied off of us and that was our idea and blah, blah, and then I acknowledge that because I am that student. I am that student who's like, that was my idea. Like they copied me and I'm the smart one. I don't say that last part I wouldn't say, but I would be really upset if someone copied my idea, particularly if they managed to execute it better than I had. So this is, again, another great place where STEM ideals can come into play. I do say like, oh, I totally get that. When you come up with a great idea and somebody copies it, that doesn't feel good. And then we talk about a couple of things. Okay. Well, one is the idea of collaboration, because that is one of the STEM ideals. And in this case, I might say, like, well, yeah, that's fine with our group. We're working with our group, but this person's not part of my group. I'm not collaborating with him. But the idea of science is really much broader, right? That we should be, even if we're not directly collaborating, we are building on each other's work. That's another of the STEM ideals, building on prior work. And one of the things that I have found has really helped, because none of that really makes them feel good. Like we talk about, collaboration is important and building on prior work is important. And overall, that idea of building on work that you've seen before is only going to lead to better results for everybody. You could bring in the idea of competition in a way if you wanted to, although I don't think it's necessary here. One of the things that I have found has worked beautifully is something that actually goes in with the be ethical STEM ideal, is I'll ask students when they present, if they have copied somebody else's idea, or if they were inspired by somebody else's idea, which is a friendlier word to use, because a lot of times, it's not a direct copy, but you can see enough elements that that like, oh, they got that idea from this other team. I'll ask students, if you happen to see something in another group that inspires you to do something, give them credit. You would be shocked at how simple, this one simple thing, when they go to present and they say, oh, well, I looked over and I saw that, Misty in this group had, maybe they don't even know maybe they just say Misty's group because they don't know who did it or whatever. And they say, oh, we looked over at Misty's group and we saw this, and that made us think about doing XYZ, or that gave us the idea to blah, blah, blah. Just that little piece of giving credit to wherever they got their inspiration from is so helpful in diffusing any of the animosity between the teams, because a lot of times it's just that people are like, I had this great idea and I want credit for it. They should get credit for it, right? So I encourage them to do that. Encourage them because it also helps you with the idea of plagiarism, in their writing and in their reports as they're going down the line. And it's also just, it is being ethical. It wasn't your idea, and that's okay that it wasn't your idea because, we live in a society where you can't copyright an idea anyway. An idea by itself, they didn't patent anything that's going on in the classroom, right? We're working at advancing science together as a class. We're collaborating. All that like kumbaya stuff is nice, but for like a student like me, that kumbaya stuff actually just like it makes me angrier. But because I'm like, I need someone to acknowledge that I had an amazing idea. So if you just get the students in the habit of that, it can diffuse the situation so much. You just say, I got this idea. We got this idea from them, blah, blah, blah. And it's also, obviously, it's just the golden rule in general, right? So that might be even a good thing to talk about before you start STEM challenges at the start of the year or whatever, if you think of it. Most of the time, I don't think of it until it comes up. And then we just talk about it then. We just use those teachable moments when they come up. But that will usually work like 9 times out of 10. It's really just about someone like being really proud of their idea. And then especially if the group that copied them gets to present first, that will just like make them insane. And you won't always catch it, right? You won't always see what they see. And so you might let the group go first that copied. And so you just need to really encourage them to give credit where they have picked it up. And just the idea that they don't need to cover that up. Like, it's okay to have been inspired by somebody else's idea to build something that you're doing right now. Just tell us who you got the idea from, because you want to give them credit, because you would want to get credit if it was, your initial idea. And what they do with it is going to be different anyway. So we can kind of talk about that and how that leads to advances and like technology, open source software, all that other kind of stuff, right? And then let me see, is there anything else? I think I've covered everything I had intended to today, except the raffle copter stuff. So, every week I have been doing a freebie for Failtober, and I was trying to figure out what do I want to do this week. And so what I decided is I will not give something this week, but I'm going to give multiple things next week through a raffle copter. So some of the things I want to do to sort of celebrate our month, I'm going to basically give at least 3 prizes next week, and I might do more. It'll kind of depend on how many people register for it. And I'll share a screen with you to show you in a second. Actually, maybe I'll do that now. Let me pull it up because I can't remember what the prizes are. So if I can pull it up, then I'll be able to see them and I won't have to think about it so hard, right? Why can't I bring up my internet? There it is. Okay. So let me share my screen with you. I'll show you this real quick. Oh, I got to pull this off. Come on. It's not letting me pull the thing off. Oh, because I've got I'm sorry. This is always like so embarrassing when I get to this point that I can't share with you something. Okay, so I'm going to pull at least 3 winners next week, and then you'll get to choose your prize. So I'm going to do a STEM Challenge 5-pack bundle. So any of the 5 packs in my store you can have. So any of the seasonal ones or the Planetopia project, you'll just let me know. Or I'm going to be going over some STEM resources next week to go along with Failtober. A lot of books I'll be going through and some articles and some other ideas that I come across that might be good for you to have in your classroom to help sort of work on these mindset pieces that are really crucial for students to build that grit, determination, resilience, and a healthy relationship with productive failure. And then, of course, one of my favorites is the 1,000 pipe cleaners. So I will do at least 3 people, but if you all, you're welcome to choose whatever you like for your prize. And what I'm going to do is right after I jump off of this, I'm going to put the raffle copter in the, I don't think I showed you that, but that's okay. I'm going to put the raffle copter link in the comments. And the ways that you enter is, I think it's like if you're following the store on the subscription list for email, subscription list to my YouTube channel, but all the links are there. And if you're already, like some of you might already be following the store, then you're already in. You don't need to do anything else other than just like register for those, I guess they're like points or whatever. They're kind of like raffle tickets in. And I'm going to pull those next week at the end of the live. So next week, again, I'm going to be doing the resources. We'll do sort of a recap of some stuff. I'll pull some prizes. I also need to pull, I didn't give my 1,000 pipe cleaners to my subscription list like I usually do last month. So I need to do last month and this month. So at least the 3 normal prizes and then 2 from the email subscriber list as well for the pipe cleaners. And I guess that's everything. I'm really excited to have been going through this month with you, and I hope that it's been helpful in some way. And if you have any comments or questions, particularly with today's session, because it's the most important one, because this is where you actually really get to implement all the things that we've been practicing, and where it can go south, but it doesn't have to. And I don't know, so much of that is just about your preparation, and just knowing what you're going to do and how you're going to react if things go south with your lab or STEM challenge. So, hi Karen. I guess that's it. So I will see you guys next week. Actually, I might not see you because I know it's Halloween. So you might be watching it after the fact, but I will be here even though it's Halloween, and I'll see you then. Bye.